Hey everyone, in this video we're going to be talking about the Daylight Hours Lab. I'm going to go through a general overview of what the lab is and what the lab write-up should consist of, and then I'm also going to show you an example. So first up, this lab is about sinusoidal models and using our knowledge of sinusoids to model the number of daylight hours a city has over time. So we're going to be collecting data, creating a graph, creating an equation, and summarizing our findings. Okay, this lab is going to be worth 20 points in the summative category. Okay, so you can choose to organize your lab however you want, but it needs to include these components. First of all, a purpose. That's a general statement, one sentence, two sentences, in which you talk about the purpose of your lab and what it's going to cover. Then we have the procedure section. This is a few sentences in which you talk about the location of your city, where is it located in the world, how close to the equator is it, longitude and latitude, those sorts of things. And then you're going to explain in words the general process for finding your values. So how did you calculate your sinusoidal equation? How did you approach it? What sort of data values were important to you or most useful to you? What sort of mathematical skills did you use? But again, this is in words. Okay, the numbers part of it comes in the data and calculation section. So first you need to show the data that you used. A table would be a great way to organize that data. Make sure that your data covers the span of a full year. We don't want to look at just 1 month because that's not going to give us enough variety of the daylight hours that city experiences. Also in your data, make sure that you're careful with the calculations of the hours of daylight. So if a city experiences 15 hours and 45 minutes of daylight, that's not going to be 15.45. 45 minutes is not 0.45 hours. So you need to make sure that you're considering 45 out of 60 minutes for the decimal conversion. So 15 hours, 45 minutes would be 15.75 hours. So careful there. In the calculations portion, you're going to show step by step how you mathematically found the different values within the sinusoidal equation. So how did you get the values A, B, C, and D? Then we're going to have the graph, and the graph should include both a scatter plot of your data and the sinusoidal model over the top of it. So it should be kind of like two graphs in one. Okay, so plot your data from the table and then the equation over the top of it so we can see how well your equation models that data. Next up is the conclusion, so write the final sinusoidal equation that you found for your city. And then finally we have the reflection. So in the reflection, you're going to write 3 conclusions or insights that you found based off of your sinusoidal model. So for example, your amplitude, what does that tell you about your city? Or your phase shift or your baseline, what does that tell you about your city? What information can you gather about your city based off of those numbers? Then I have a couple websites that can help you. Of course, you can use other websites, just make sure that they're reliable. All right, so I'm going to quickly run through an example with you, and I'm going to choose to look at Minneapolis. So your daylight hours lab should not be Minneapolis. It should not match the data that I'm showing in this example video. Okay, so when I'm looking at the data, you're going to need at least 15 data points, and you're going to need it to span 12 months. If you look at just 1 month or even 6 months, you may not see the full range of daylight hours that city experiences. So here I have just 2 points of data, but if I were to want full credit on this lab, I would need at least 13 other data points. The 2 points that I've picked here are the 2 that I'm going to end up using for my calculations, and I've picked them because these 2 represent the maximum and the minimum amount of daylight hours that Minneapolis experiences on average. Okay, when you look at these values, you'll notice that I've converted them a little bit from the blue original values that I wrote down to the purple, and the purple is what I'm going to actually use in my calculations to try to be a little bit more consistent. So as far as the date goes, I converted them from June 20th and December 24th to the day number that they are in terms of like how many days into the year is that date. So June 20th is day number 172 out of the year, and then December 24th is day number 359. Okay, and then you'll also notice that I've converted to a consistent unit in the hours of daylight, my Y value. So 15 hours and 36 minutes is how much daylight Minneapolis experiences on average on June 20th. 8 hours and 47 minutes is for December 24th. And that kind of matches up with what we've experienced, right? In the summer, a lot longer days, a lot more sunlight, winter, much shorter. Okay, but you'll notice that 15 hours and 36 minutes is not 15.36 hours, right? We can't just plop in a decimal point there in the middle, right? Because 36 minutes is more than half of an hour, so it should be more than 15.5. So to calculate 15.6, I took those 36 minutes out of the 60 minutes in an hour. So 15 plus 36 over 60 gives me 15.60 hours. Okay, same thing for 8 hours and 47 minutes. 47 minutes is more than half of an hour. So I took 8 plus 47 sixtieths to get 8.78 hours of daylight. Okay, so again, you'll need 15 data points spanning at least 12 months. Take time to do those conversions, and then you're going to want to pick out the maximum and the minimum values from that data set. All right, and thinking about this sinusoidal model, I'm going to need 4 values to transform that parent function into one that models this data. 2 horizontal changes and 2 vertical changes. To help me out, I'm going to create a quick sketch of what my data looks like. So I'm going to draw a quick XY axes and plot these 2 important points. So starting with the maximum hours of daylight, which happens 172 days into the year. Okay, and that's 15.6 hours of daylight. And then the minimum happens 359 days into the year, and that's 8.78 hours of daylight. So what I really have is actually half of this wave going from the maximum down to the minimum. I can imagine that the following June, right, would be another maximum, so that graph is going to continue to oscillate up and down as the years continue. All right, so first up, I'm going to calculate the baseline, which is that new middle of the graph. Now, our original baseline for the parent function would have been at 0, so this change is going to represent a vertical shift. Okay, and I want the halfway point between the minimum and the maximum hours of daylight, so I'm going to take the average of those 2. So I'm going to take the maximum plus the minimum and divide it by 2. So that's 15.6 plus 8.78 divided by 2, which is 12.19. Next up, I'm going to calculate the amplitude, which is going to give me the vertical stretch or shrink. Okay, the amplitude is normally 1, and that's the distance between the baseline and the maximum, or the baseline and the minimum. So you can calculate it a couple different ways. You can take one of those extrema and just find the difference between that and your baseline value, so the maximum minus d. Or you can take half of the range. So the range would be the distance between the extrema, and we want half of that. So you could also take the maximum minus the minimum and divide it by 2. So I'll do that second option. Okay, so I would get 3.41 as my new amplitude. All right, next up are the horizontal changes. So I'm going to think about the period length first, and that's going to help me find this horizontal stretch or shrink. Now, this isn't a full period going from the maximum down to the minimum. That's half of the period length. So I'm going to have to double it to find the full period. Okay. So if I take 359 minus 172, that will give me how many days are in this half period. I get 187. Okay, if I double that, I get the full period length, okay, which is 374. Okay, so a little bit longer than a full year. All right, so then the b value isn't equal to the period. It's 2 pi divided by the period length. So I'm going to take 2 pi divided by 374. Since 374 is divisible by 2, I'm going to simplify that to pi over 187. All right, last but not least, we have the shift, okay? And I chose cosine because cosine starts at the maximum. Right, so if I can just calculate the shift to that new maximum location, I can calculate that C value. Okay, so since my maximum occurs 172 days into the year, right, this shift is to the right 172, so I should have x minus 172 in the horizontal shift position. Okay. And now I have all of the values that I need. Okay, this would constitute the calculations portion of my lab write-up. Okay, and then in the conclusion, I'm just going to plug them into the function. So I have 3.41 times the cosine of pi over 187 times x minus 172 plus 12.19. Okay, and that would be my sinusoidal function. For the graph, I wouldn't want to use my sketch, although I'm going to include that in the calculations portion. My graph should be a little bit more clean, a little bit more professional. So in Desmos, I'm going to type in my sinusoidal equation and plot my data points, okay, the 15 data points that I collected, so I can compare how well my sinusoidal model matches that data. Okay, and of course there are other sections of the lab write-up to include the paragraphs or short sentences about the procedure and my reflections that I want to include as well. But hopefully this is helpful to get you started for your daylight hours lab.